This example is going to go through how to find how fast a car can travel around a curve without crashing. So we have a car, and this is a bird's eye view that's going around this turn. We have a radius of 40 meters, and if we think about this, the forces that are acting here, right? So we're going to have gravity facing down. We have a normal force up, and those two forces are going to be equal in size. And then we have our frictional force here, and our frictional force actually is acting towards the center of our circle. If there was no friction, most people think, well, isn't friction pointing out? But no, it's actually pointing in. It's the friction of the tire on the road that's actually pushing you towards the center. So a bird's eye view from here, right? We have our frictional force pointing towards the center. Because it's circular motion, we also have a acceleration pointing towards the center, and then our velocity, our tangential velocity, would be pointing in this direction at this moment. So what we're going to look at is just the idea that we're going to use the net force equations to solve this problem. So we could do the net force equation in the vertical or in the y direction. That would just be the normal force minus the force of gravity equals mass times acceleration. And in this case, this acceleration would be 0. And what that proves is that normal force is going to equal my force of gravity, which is what we already said, and we already understood that because we're not accelerating up or down. So now the rest of it is you doing the same thing with the horizontal motion. The only force acting in that direction is going to be my force of friction, and that's going to equal mass times acceleration, and that is a centripetal acceleration because it's perpendicular to my velocity. So that's why we can now call it AC. So as we go through this then, because it's AC, we can say this is a centripetal force as well, which again, this is not its own force, but it's the net force that's acting perpendicular to the velocity. And in this case, it's just due to friction. But we know AC is V squared over R, so we can then plug this in here for AC. When we do that, then we can rewrite this as the force of friction is mass times velocity squared divided by my radius. Now, I want to figure out how fast I can go, and I just have the force of friction here. So what I can understand is that my force of friction, that equation is the coefficient of friction, or mu, times the normal force. And we've already shown that normal force is equal to the force of gravity. So, and we know that the force of gravity is mass times gravity. So then I can take all of this and kind of plug it into this left side. And then I'm going to write it as the coefficient of friction times my normal force, which is mg, equals mass times velocity squared divided by r. Now I can get rid of mass on both sides. I'm going to get r to the other side by multiplying it by both sides. And then I'm going to square root this velocity and just get that my velocity max is the square root of the coefficient of friction times gravity times the radius, or as I learned it back in the day, radical rug. So radius times the coefficient times the acceleration of gravity. So that's the way that we would set that up with circular motion. And the cool thing is really it doesn't matter the size of the vehicle. The mass doesn't play a factor. So all vehicles would have a similar velocity max. And so that's why when you look at the kind of on-ramps and off-ramps, right before you go onto it, you might see a sign over here that says, maximum velocity 35 miles per hour, right? And so more than likely, you could actually go faster than that, but that's going to be universal for all vehicles due to mass not playing a factor.